Lab 4 consisted of learning how to use percent difference and percent error. Given our information and overall knowledge of acceleration, we changed our acceleration from Lab 3 by either increasing or decreasing the theoretical acceleration using a change in one of the masses. Overall, we used those two formulas to see if we met our overall goal and to ensure quality of our experiment. This is a good guide I found published by the University of Columbia. It went over certain types of errors, such as ones we use to quantify uncertainty, and really it emphasized the importance of experimental errors um, when it comes to interpreting our results, and that no measurement is always going to be exact. There's always going to bound to be error, and instead of looking at this as simply mistakes, we can see them as key points in which we can understand our data's limitations. By comparing theoretical and experimental accelerations, we see how accurate and precise our setup and calculations were. This is important in things like car crash testing, where percent error can tell engineers experimental how close the experimental results were to the expected values. It can ultimately help them improve safety features and the vehicle's design if needed.
The materials used for this lab were the Pasco/Capstone application software. This was used to create the graphs that will be later presented in this report. We also used the triple beam balance, and this was to weigh the mass, the hanging mass. We use a passport motion sensor. This was to sense the motion as it approached and was away from the sensor. We used an air track and a glide. This is used to create the graph, and a laptop and scientific notebook for observations.
For this procedure, firstly, we calculated the new theoretical acceleration values, and we also calculated the new masses for the glider car and along with the weights, and used the new weights in this experiment. The experiment was conducted in the same way as experiment 3, where the glider was pushed away on the air track, but the weight would bring it back, causing it to bounce and recoil and create the new graphs. After performing the experiment, we then calculated the experimental values and compared them to the theoretical values by finding the percent error between the variables.
To start our lab number 4, we did follow the procedure and we did our setup. But we also used the information that we had originally from lab 3. So our old values are what we had created. So the 0.69, 14.8 grams, and the glide mass of 194.4 grams. So for our new ones, the glide mass stayed the same, but the hanging mass did change. We did add weight to it, so it changed to 49.85 grams. And then again, we changed our acceleration to 2.0. So our hanging mass is our glide mass times our acceleration over gravity minus acceleration. So our new hanging mass was 49.85 grams. And then our glide mass, which is our hanging mass times gravity minus acceleration over acceleration, the new one was 194.42 grams. Using a similar process from the previous lab, number 3, we calculated or we got our old theoretical acceleration of 0.69 meters per second, and then we calculated our new theoretical acceleration using the same formula of the hanging mass times gravity divided by the hanging mass plus the glide mass. And then that's how we got the 2.0 meters per second squared. And our percent difference is the reference value minus the tested value divided by the reference value. So far we did get a big percent difference of 190. But I believe the increase was also because our mass did change. So therefore, not only our mass, our hanging mass, but also our acceleration. So all of those play into a factor why there's such a big difference. After a couple of tries, we were able to create our position versus time graph, the one that you see here, and then based on that, we created our acceleration graph. So we did pick the second hill, and that's where we started to annotate it. So this is the beginnings of our annotations to that graph. But overall, you can see the consistency in our position versus time graph and the acceleration, how it does follow the increase and then the little constant and then decrease again, and the change acceleration as it's changing direction on the air track. This is our same graph. Our graph number one is just once we finished the annotations, we had the 4 points, and then we also had our acceleration between point 2 and point 4. So that way we could better see our acceleration using the graphs. So based on our points in our graph, we then went to find the lab percent error. And the percent error is the percent of a value that is off from the theoretical value. So our original theoretical value was 2.0 acceleration. Our experimental acceleration was negative 1.59. So that just means that our acceleration was going the same, maybe, or almost the same, like potential acceleration, but it was negative. So it's also showing that instead of just like the velocity might have not been increasing, but it was more decreasing, which would make sense because as it was going down, it did change the velocity. But our percent error was 20.5. And then the percent error formula is the experimental value minus the accepted value divided by the accepted value times the 100 to get the percentage. And then for our final table, we calculated the percent difference, but this is from the actual accelerations that we did get. So it was a 0.69 our original. Our change that we had gotten from the graph, the acceleration was negative 1.59. And so the percent difference is 130%. Our original was 190%. But I feel the differences can be shown from our original theoretical was theoretical, and then our theoretical was of 2.0 acceleration, and then this is a negative 1.59. So it is a difference either way, but again, it's going in the negative direction, and it's a slightly smaller number than 1.59 is smaller than 2. So that can also account for like our difference not being as big as originally was thought to be. Because again, the percent difference is the percent a value has changed from its original value. So either way, our acceleration did change from the original acceleration. Ideally, our percent error from our previous one should be small. We had gotten a percent error of 20. So it was small, but it's not as small as it could have been. Like it would have been preferred to have been in the single digits rather than the double digits, the 20.5. So that does show that we did get close to accurate, or we tried to get as close to accurate. But we did have differences in our reading, of course, because the sensor can feel the air was the sensor itself. The track is running on air, and then different vibrations from either us talking or the table and such can change the what the sensor had written, what it created in the graph. And because that's what the sensor had seen, we might not always feel or know what exactly the forces of the sensor. Plus, the sensor might have been faulty, and in the sense of it did create our graph and it was pretty smooth, but it could have also gotten other information that we might not have intended it to get as well. But again, that's something that is out of our control, but we can just try to get as accurate measurements and as accurate percent error as we can. So overall, the small
In this lab, we explored how acceleration depends on mass and force and how experimental results compare to theoretical problems. So, what we've seen in previous labs, we get to explore the relationship between force, mass, and acceleration using real world examples of a glider, pulley, and hanging mass. And we get to view the percent errors to determine our experiment's accuracy. So, going into the question, should these percent differences be similar? Why or why not? So, yes, ideally, but a lot of factors can come into play, like friction in the pulley, friction between the glider and track, sensor reactivity, for example. Compare your percent differences. Are these values similar? How much? So, they aren't very similar, but that could be to a difference in values, which can be contributed to the factors I previously mentioned. They differ about 59.6%, with the experimental being lower. So, does this agree with your ideas in the previous questions? Yes, the ideas align since imperfect experimental conditions would make the measured change smaller. And what can you conclude from these values? The percent error was on the lower end, so we believe the experiment went okay. We just had different values, which overall indicates systemic loss or measurement issues. So, thank you.